Hello everyone. My name is Pranay Teja Chintakunta and I am here with my teammate Pavan. Today we are presenting our project for the Evolutionary Computation module where we implemented a complete genetic programming based on classifier to predict income categories from the modified adult dataset. This project requires us to design a full machine learning pipeline based on entirely evolutionary computation principles, where we trained a genetic programming model, evaluated it, and finally submit the prediction to Kaggle. We are excited to walk you through each stage of our work. Now discuss about the slide problem statement. The main objective of this assignment was to classify whether an individual earns more than $50,000 annually using only genetic programming or grammatical evolution. We were provided with a training and test dataset in CSV format. Our goal was to create the GP model to generate predictions for the test set and upload them to Kaggle competition. Unlike traditional machine learning models, GP requires a very different way of thinking because instead of tuning weights, GP evolves symbolic expressions. This made the problem both interesting and challenging. Now let's discuss about the dataset description. The dataset contains demographic, educational, and work related attributes. Some examples are age, work class, education level, marital status, capital gain, hours work per week, and occupation. The target label is binary. 0 for individual earning is less than or equal to 50k and 1 for those earning more than 50k. This dataset, originally from the UCI repository, is widely used in classification benchmarks. However, the version provided for the competition had been modified slightly, which required us to explore it carefully before modeling. Now let's discuss about the challenges we faced in the dataset. There were several challenges that needed attention before applying GP. First, many rows has missing values and we represented as the string question mark, especially in the fields like work class, occupations, and native country. GP doesn't handle missing or non-numerical values directly, so we had to clean the dataset thoroughly. Second, the dataset contains a dozen categorical columns with multiple categories, which cannot be fed directly into genetic programming. Third, numerical features span very different ranges. For example, hour per week ranges from 1 to 99, while capital can go up to thousands. Without scaling, GPU operations like multiplication and division can behave unpredictably. Lastly, there is a mild class imbalance, which means models might favor the majority class. We needed to ensure genetic programming doesn't get stuck predicting the dominant label. Now let's discuss about the data preprocessing pipeline. To address these challenges, we built a structured pre-processing pipeline. We started by replacing question mark with NaN so they could treat it as genuine missing values. Then, for every categorical column, we filled missing values using the most frequent category or mode, which works well for discrete features. Next, we applied encoding to convert all categorical values into numerical form. Unlike one hot encoding, label encoding produces a single integer for each category, which is more suitable for GP because it keeps dimensionality low. To ensure consistency across numerical features, we scale values using MinMax Scaler, transforming every value into the range of 0 and 1. This step is so crucial because GP combines features through arithmetical operations. Unscaled data could lead to exploding values. Finally, we separated Xscale trained Y trained, and X test scaled, which allowed genetic programming to run smoothly. You guys know that why genetic programming? Like we selected genetic programming because of its unique capability to automatically discover mathematical relationships in the data. GP evolves trees that represent symbolic expressions, allowing it to learn complex decision boundaries without any manual feature engineering. Unlike traditional machine learning methods, genetic programming does not rely on gradient descent or convex optimization. This means it can explore a much larger search space without getting limited by local minima. Another advantage is interpretability. GP produces a symbolic equations which can theoretically be analyzed to understand how the model make decisions, although complex trees can still be hard to interpret. The idea of learning symbolic models remains powerful and interesting. Now let's discuss about genetic programming system design. To make GP expressive enough, we constructed a robust primitive set. This includes basic arithmetic operators like addition, subtraction, multiplication, and protected division function to safely handle division by zero. We also included non-linear transformation such as sine, cos, and neg. This allows GP to model periodic or sign-based relationships that simple linear models cannot capture. The conditional primitive if then else enabled genetic programming to incorporate decision making logic inside symbolic expressions. Our terminal set our terminal set consists of all input features represented as argo, arg1, arg2, and so on, and inferior random constants sampled from -1 to 1. We also initialize trees using the half and half method to ensure diversity and applied strict bloat control by limiting the tree height to 70. So this is my side of presentation. Now my friend and my teammate Sai Pavan will continue the presentation. Over to Sai Pavan.
Thank you, Pranay. Hi, this is Sai Pavan Ganapuram. Now, I will walk you through our training configuration. We used a population size of 300 individuals, which provides a good balance between exploration and computational cost. We also evolved the population for 50 generations, which allowed enough time for GP to optimize expressions without overfitting. Crossover probability was set to zero point 0.8 so that the most new individuals are created by recombining the already existing ones. The mutation probability of zero point 0.2 ensured enough randomness to keep the search space diverse. And we used tournament selection with size 3 for selecting individuals. This method selects the best out of 3 randomly chosen individuals, giving the fitter solutions a higher chance of reproduction. Our fitness function was straightforward. The classification accuracy was on the training data. The Hall of Fame stored the single best performing individual across all generations, ensuring we never lost the top model. Now, moving on to the next slide. Here is how the evolution process works in practice. In every generation, each individual tree is compiled into a new Python function using DEAP's toolbox.compile method. This function is then evaluated on every training example to generate predictions, and these predictions are converted into binary labels using a threshold of 0, and accuracy is computed against the true labels. And once the fitness values are assigned, tournament selection chooses individuals based on their performance. Crossover then recombines two parent trees by exchanging subtrees and also by producing new and sometimes more complex logic. the mutation randomly modifies parts of the tree, helping the search space local optima. This cycle continues for 50 generations, and over time, the population becomes increasingly specialized. Meanwhile, the Hall of Fame preserves the global best individual. The best individual discovered by the GP process turned out to be a highly nested symbolic expression. It combined arithmetic operations, trigonometric transformations, conditional statements, and feature values in complex patterns. Even though the expression is extremely long and not easily interpretable by hand, this level of complexity is quite common in GP when dealing with real world datasets. But what matters is that the symbolic structure is automatically tailored to capture subtle patterns across multiple input features. Now, moving on to the results, our final model has achieved a training accuracy of 82.94%, which indicates that GP successfully learned complex decision boundaries without overfitting too much. We used the best symbolic expression to generate predictions for the test dataset and submitted them to Kaggle. Our final Kaggle score was 0.76474, which is competitive considering the difficulty of the dataset and the fact that we only use GP and not any other standard machine learning methods. The submission contained 9,769 predictions in the correct format. Overall, the GP approach performed strongly. Now, moving on to the pipeline. This diagram summarizes our entire solution pipeline. We begin with raw data loading, followed by pre-processing that includes cleaning, encoding, and scaling. Next, we configure the GP system with its primitive and terminal sets. We also initialize the population and begin evolving individuals through 50 generations. Once the evolution ends, the Hall of Fame provides the best expression, which is compiled into an executable function. This function is then used to generate predictions for the test dataset. And finally, we submit the generated CSV file to Kaggle. This pipeline ensures that the entire process is automated end to end. Now, moving on to the strengths and limitations. Genetic programming brought several advantages to our project. It is highly flexible and capable of discovering non-linear relationships automatically. It also allows symbolic reasoning, which is something many modern machine learning models lack. However, the GP also has limitations. It is computationally heavy, even with the 300 individuals and 50 generations. The training required significant time. GP expressions tend to grow large, and while we used height limits, some evolved trees were still extremely complex. Another limitation is interpretability. Despite being symbolic, the final expression was too long to understand meaningfully. Overall, the strengths outweighed the limitations for this project. As we talk of the future improvements, we believe multiple objective GP would greatly enhance our approach. By optimizing both accuracy and simplicity simultaneously, we could reduce the model's complexity significantly. We also plan to explore grammatical evolution, which uses a formal grammar to enforce structure in the generated expressions. Also, parallelizing the fitness evaluation could drastically reduce computation time. Finally, creating an ensemble of GP models could improve stability and predictive performance. To conclude, we have successfully designed and implemented a full genetic programming pipeline for income prediction. Our model achieved strong performance, both in terms of training accuracy and Kaggle evaluation. This project allowed us to work deeply with evolutionary computation techniques, symbolic modeling, and pre processing workflows for real world data. Overall, the GP proved to be a powerful tool for our classification tasks requiring creativity in model structures. So, thank you for listening to our presentation. We hope you have enjoyed it. Thank you.